So this video is for applications of forces for A2 mechanics. We're looking at 4.1 in the notes, which is static particles, and focusing on this idea of equilibrium. It works, there's nothing new really in these examples, so it's working using F equals ma, which we've already looked at previously. And when we're using F equals ma, if we are in equilibrium, then we have got A is equal to 0. So we can use exactly the same process that we've used previously in order to find out what that resultant force is. There's a number of different ways to tackle this question, so it's up to you whether you decide to go along a certain direction or whether you just decide to go horizontal and perpendicular. Basically, the two directions that you choose need to be perpendicular to each other for this to work, which is exactly the same as the inclined planes and pulleys that we've seen previously. So if we have a look at this first example, what I'm going to do here is I'm going to go horizontally, and we're going to look at it as though we're setting up F equals ma. So if I'm looking in the horizontal direction, so coming along here, I'm going to take to the right as we're looking at the screen to be positive. So this angle here is 30 degrees, giving me this angle here to be 60. So if we focus on each force, so we've got P, it needs resolving, so that's coming round to here, that will be cos 60. 2, cos 30, positive because it is going in the same direction as the P force. 4 is also positive, and then that would be cos 60. And then we've got Q acting in the opposite direction. So I'm going to subtract that off. It doesn't need resolving because it's acting in that direction already. So this is how we would set up F equals ma. Go through each force, count how many forces you've got working in that direction. So I've got 1, 2, 3, 4, and I should have 4 terms within this expression here in order to make this work. And then I can set that by letting acceleration equal 0. We end up with this equation. So tidying that up a little bit, we've got P over 2 plus root 3 plus 2 minus Q is equal to 0. Doing exactly the same, looking in this direction. So vertically we've got P sine 60 plus 2 sine 30. 4 is acting in the opposite direction, so these two are both acting upwards. I'm treating this almost like it's the origin, so it's like I've got some axes on there, and if that's the origin, then this one, if you were thinking about its coordinate, we've come across positive on the x, so that's positive horizontally but negative vertically, so it's going to get minus 4 sine 60 is equal to 0. Q is acting perpendicular to that direction, so it doesn't need to be included. So P2 and 4 are the only forces that I need to include. So working with this blue equation, we can go on to solve this. So we've got root 3 P over 2 plus 1 minus 2 root 3 is equal to 0. That leads us to P is equal to 2.85 newtons to 3 significant figures. Now, in terms of your calculator, you need to have the exact value, which is 12 minus 2 root 3 over 3. That needs to be kept into your calculator because we're going to be using this in the red equation in order to be able to solve for Q. So do watch that. We have to give our answers to 3 significant figures in terms of the exam, but I do want to use the exact value when I'm substituting it into here. So into this equation down here, that leads us to Q is equal to P over 2 plus root 3 plus 2, which when we calculate that is 5.15 newtons to 3 significant figures. Again, your exact solution there is 12 plus 2 root 3 all over 3. So there should be nothing new there. You can use here, you could have gone for cos 30 and cos 60 here and cos 30 here. So you could have gone for that instead of using sine. It just depends which way you've got used to doing it. It doesn't matter. What you are looking for in terms of doing these questions is making sure every force is present and any forces that need resolving have been resolved. So if we have a look at the next example, again, we are working in equilibrium, so it's F equals 0 in terms of F equals ma. I'm going to do exactly the same thing, but this time I'm going to work along the plane. So we'll take that to be the red direction. So any force that does not lie on that red line and is not perpendicular to it will need resolving. So if we put both of the directions in, blue's not showing up very well there, never mind. So any force that does not lie on one of those two lines is going to need resolving. So that's the P and that's the 5. That means that both of those need to be included in both equations when you're setting this up. Often students miss out one of these forces when trying to resolve in one of the directions. So it's something just to watch for. That angle there between 5 and the perpendicular is 30 degrees. So setting up, let's go parallel to the plane first. So acting down the plane, I've got 8 plus 5 sine 30. Could have used cos 60 at that point if you wanted to. P is acting in the opposite direction, so that gets subtract and it needs resolving because it doesn't lie on the red line. So that's P cos alpha. And we're in equilibrium, so acceleration equals 0. And looking along that line, I've got one force lying on that line, and then I've got two forces that don't lie on either line. So I know I've set all of those up properly. That simplifies down to P cos alpha equals 10.5, which is exact value. Perpendicular. So we have got 2 acting upwards and P is acting in the same direction, so that's positive. Sine alpha, you can write this as cos of 90 minus alpha if you want to, but then you would have to recognise that that's sine alpha when we're continuing with the question. 5 is acting in the opposite direction, so it gets a subtract. So minus 5 cos 30 is equal to 0. So solving this for P sine alpha, we've got P sine alpha is equal to 2.33. Again, the exact value here, so you'd keep this stored on your calculator. Please make sure you know how to store on your calculator, is 5 root 3 minus 4 all over 2. So that's what we've got there. So in order to find P and alpha, I'm going to use the same method as what we would use if we were in pure doing r cos of x plus alpha. So if I divide the two equations, so if I do this equation, the blue equation divided by the red equation, we end up with sine alpha over cos alpha, which is going to give me tan alpha. So tan alpha is equal to 2.33. Remember, on my calculator, I've used the exact value. Inverse tan on that is leading to alpha is equal to 12.5 degrees to 3 significant figures. this time, rather than using that value, just in case I've got it wrong, and because I have got the option to use a different method, I'm going to go for squaring both of these. So if we square the blue equation, square the red and add it, we can factorise out p squared. And that leaves me with sine squared plus cos squared inside the bracket, which is equal to 1. So I've ended up with that. So I'm using sine squared plus cos squared. So this squared plus this squared is equal to p squared sine squared plus p squared cos squared. Factorise out the p squared, leaves me with sine squared plus cos squared in the bracket, which is just 1. That's where that's come from. And this implies that p is equal to 10.8 to 3 significant figures. There we go. If you've worked out alpha and you've got 12.5, you are okay to substitute it back into one of these two equations in order to find p. That is not a problem, but just be aware that if you have made a mistake with that alpha, then you wouldn't get follow-through marks on this, because there is a way to go about it without using your value, and that tends to be how that is worked.